and where simply walking down the street would be an impossible task. It sounds crazy, right? But every single movement you make, from the beating of your heart to the planets orbiting the sun, actually follows just 3 incredibly elegant rules. Today, we're exploring Newton's laws of motion, the 3 rules that move the universe.
Okay, let's dive right into this. Have you ever wondered why you lurch forward when a car brakes suddenly? Or, why an empty shopping cart is just so much easier to push than one loaded up with heavy groceries? Well, the answers to these relatable, everyday experiences are the exact same principles that guide massive spacecraft through the cosmos. By the end of this explainer, I promise you're going to look at your everyday movements in a completely different light.
Here's a quick roadmap of where we're headed today. We'll kick things off with the historical context of these rules. Then we'll break down the first, second, and third laws of motion one by one. After that, we'll look at how these laws apply to modern biomechanics and flight, and we'll wrap up with the ultimate physics showdown, Newton's legacy versus Einstein's theories.
All right, let's set the stage and look at the world before these 3 rules changed everything.
It's kind of wild to think about, but for thousands of years, people assumed motion just naturally died out. If a horse-drawn cart stopped moving, observers just thought it was because motion was temporary. But then, in the 1600s, scientists like Galileo Galilei came along and showed that objects actually tend to keep moving unless something interferes with them. Building directly on that brilliant insight, a young Isaac Newton published his famous Principia in 1687. What made his 3 laws so absolutely revolutionary was that they proved the exact same mechanics govern the Earth and the heavens. The physics dropping an apple to the ground, it's the exact same physics holding the moon in orbit.
So, let's open up this universal rulebook, starting with rule number 1.
Newton's first law is known as the law of inertia. It states that a body remains at rest or in uniform straight-line motion unless acted on by a net external force. So the crucial point here is that objects are, well, stubborn. They simply want to keep doing exactly what they are already doing. If an object is sitting perfectly still, it wants to stay still. If it's moving at a constant speed in a perfectly straight line, it wants to keep doing exactly that forever, unless a completely unbalanced outside force makes it change.
And you actually use and fight against this inertia every single day. Think about trying to get stubborn ketchup out of a glass bottle. You swing it forward and then suddenly jerk the bottle back. The ketchup, thanks to inertia, wants to keep moving forward and voila, it lands on your burger. Or, if you're in a car that suddenly slams on the brakes, the vehicle stops, but your body wants to keep moving forward at the exact speed the car was just traveling, which is, of course, exactly why we need seatbelts. And hey, what about that classic magic trick of yanking a tablecloth out from under a fancy set of china? That is literally just inertia in action. The china remains at rest because the sudden, short force of that slippery cloth just isn't strong enough to make those heavy plates move.
Now, let's scale this up to the macro level to bust a very common sci-fi movie myth. In the movies, if a spaceship's engines die in deep space, the ship usually slowly grinds to a halt. But Newton's first law tells us that without friction or air resistance to act as an external force, that motion never dies out. A spacecraft with dead engines will just continue coasting in a straight line at the exact same constant speed forever.
All right, moving on to the second law. What happens when an external force actually does interrupt that inertia?
What's amazing to realize here is that when a net force acts on a body, that body accelerates. The famous equation for this is F equals ma. Net force equals mass times acceleration. In everyday terms, this simply means that an object's acceleration depends on 2 things: how hard you push it and how heavy it is. This is exactly why an empty shopping cart is super easy to push, but a fully loaded truck or a heavy bus compared to a lightweight race car requires massive force to get moving. It's the exact same equation engineers use today for everything from robotics to roller coasters. And this brilliantly illustrates the math behind it all. In physics, we measure force in a unit appropriately named after the man himself, the Newton. 1 Newton is exactly the amount of force required to accelerate a 1 kilogram mass by 1 meter per second squared. It's just a perfectly balanced relationship. But this equation isn't just for textbooks or engineering. It's literally happening inside your head right now. In your inner ear, there are these microscopic hair cells that sense the force they have to exert to cause tiny membranes to accelerate along with the rest of your body. Because of F equals ma, you can actually sense the magnitude and direction of your own acceleration with your eyes completely closed. And here's a quick physics mythbuster for you. There's actually no such thing as a force of acceleration pushing you back into your car seat when you speed up. That feeling? That's just your own mass, your inertia, resisting the forward push of the car seat. The car is literally accelerating around you.
Okay, let's hit the third and final rule, which shows us how forces always arrive in pairs.
Newton's third law states that if body A exerts a force on body B, then body B exerts an equal force back on body A. These two forces have the exact same magnitude, but they go in opposite directions. Put simply, for every action there is an equal and opposite reaction. You literally cannot touch something without it touching you back with the exact same amount of force. It's how you walk. You push the ground backward and the ground pushes you forward. It's how you swim. You push water backwards so it pushes you forward. Even birds fly by pushing air downward.
Now, what's really interesting here is understanding exactly where those forces go. When a soccer player strikes a ball, the foot applies a forward force to the ball, launching it into the air. But simultaneously, the ball applies an equal and opposite force backwards, directly onto the foot. This is a crucial point that trips people up all the time. The action and reaction forces do not cancel each other out. Why? Because they are acting on two completely different objects. Your foot pushes the ball pushes your foot.
This is also the ultimate secret to space travel, often called the rocket principle. A rocket doesn't fly by pushing against the ground or pushing against the air. Think about it. In the vacuum of space, there's absolutely nothing to push against. Instead, a rocket operates purely on Newton's third law. It forcefully expels mass, specifically hot gas from burning propellant, downward out of its engines. That's the action. The equal and opposite reaction is that the rocket itself is pushed upward. It literally throws mass one way to go the other way.
So, how are modern scientists and engineers actually using these centuries-old rules today? Let's take a look.
Well, for starters, Newton's second law is essentially the foundation of modern sports science. Researchers literally use F equals ma to quantify the forces in a hammer throw, helping athletes maximize their throwing speed. Whether you're skateboarding, riding a bicycle, or analyzing a soccer header, it's all just physics. For example, by calculating the exact forces involved in heading a soccer ball, scientists found that simply reducing the ball's inflation can significantly mitigate injury risks, which is a game changer for young players. They even use these laws in the gym to determine that pneumatic resistance maximizes acceleration and power, while traditional free weights maximize raw force. Athletic performance is quite literally a math equation.
And when we look up at the skies, Newton's third law is the invisible magic making aviation possible. Airplane wings, or airfoils, are specifically designed to deflect air downward as they move. The action is pushing air down. The equal and opposite reaction is the air pushing the wing upward, which creates lift. The same exact principle goes for pitching a wicked curveball. A spinning ball deflects air to one side, and the reaction pushes the ball in the opposite direction. From baseballs to massive jumbo jets, it is all action and reaction.
But what happens when Newton's perfect, everyday rules reach their absolute cosmic limits? Enter Albert Einstein. In the early 20th century, Einstein introduced his general theory of relativity, which revealed some fascinating limits to Newton's work, particularly when it came to gravity. See, Newton just assumed that gravity traveled at an infinite speed, that it was felt instantly everywhere. According to Newtonian physics, if our sun magically vanished right now, the Earth would instantly fly out of its orbit. But Einstein realized there is a strict cosmic speed limit, the speed of light. Einstein proved that if the sun disappeared, we wouldn't even notice the absence of gravity for 8.5 minutes, because that's the exact time it takes for light and gravity to travel to Earth.
Let's move on and see how this builds into an even deeper difference regarding where gravity actually comes from. Newton firmly believed that mass alone dictated gravitational pull. Einstein, however, realized that mass is just one form of energy, and all forms of energy create gravity. That means heat creates gravity, sound creates gravity, and crucially, gravity itself creates more gravity. Because of this wild compounding energy effect, the gravitational force very close to our massive sun is slightly stronger than Newton's equations calculated.
And because of that extra compounding gravity near the sun, the planet Mercury doesn't follow a perfect Newtonian ellipse. Its orbit constantly shifts around like a rosette pattern. Newton's math couldn't quite explain it, but Einstein's theory predicted it perfectly, cementing relativity as the new standard for extreme cosmic conditions. But hey, here is the absolute most important takeaway from all of this. While Einstein expanded our understanding of the universe at its absolute extremes, Newton's 3 simple laws remain incredibly accurate for our daily reality. We still use good old F equals ma to design skyscrapers, build bridges, and launch rovers all the way to Mars.
From a falling apple to the incredible thrust of a rocket engine, Isaac Newton gave us the language to understand motion itself. So I want to leave you with this final provocative thought. As you sit perfectly still right now, watching this explainer, how many invisible forces